The first problem of homework 110 is not too bad. Basically, we just got to find the steady state expression for the current through this whole circuit, I of t. If we apply this voltage source, that's 100 millivolts at the angular frequency of 50 radians per second. So we want to convert it to this cosine form so we can make it into a phasor. So all we got to do, sine, cosine are orthogonal. So sine minus 90 is cosine. So we're going to go ahead and convert this to a phasor. This is going to be 100 minus 90 millivolts. So that's going to be our Vs. Now we need to find the impedance of the circuit. So we're going to find the equivalent impedance by finding the impedance of these given frequencies and adding them all up. So 50 radians per second times 0.24 is going to be 12J ohm. I'll just put the unit for now. And then ZC is going to end up being 8 over J, which we can also write as J over, or minus J8. And if you're confused on how to do that, basically you just take the complex conjugate. It's kind of like rationalizing denominators. So multiply both top and bottom by the complex conjugate. This cancels out to be 1, so it becomes minus 8J over 1. So anyway, that's the impedance of the capacitor at this frequency. And now we're going to find the equivalent impedance. We're just going to add them all up. So ZQ is going to be 4 plus, we have 12 minus 8. That's going to be 4 plus 4J ohm. And if we want to find out the current IO, we're going to take Vs divided by ZQ. So let's see, 100, phase angle of 90 degrees. I'm going to keep the millivolts just so I don't forget about it. 4 plus, or not 4, we got to convert this to a phasor first. We don't have to, but since I have it in a phasor form, it makes it easier. So this is going to be square root of 32, which is 5.65-ish. Phase angle is 45 degrees. Tangent of 1 in the first quarter, or arctangent of 1 in the first quadrant is 45 degrees. So 5.65, phase angle 45, and it's ohms. Take that ratio, 100 divided by 5.65 is 17.67, and 100 or 90 minus 45 is minus 135 degrees, and this is milliamps. So we want it into the time domain. We're just going to take our magnitude and phase and translate it back. So I of t is going to be 17.67 cosine 50t. Frequency doesn't change, remember. Minus 135 degrees milliamps. So if you're like me, you may like working in complex numbers instead of these phasors when it comes to calculating these things. In which case, instead of it being 100 with the phase angle of minus 90, it'll be minus J 100, and then we'll have the same impedance we had before, 4 plus 4J. That's going to equal minus 12.5 minus 12.5, and this is also ohm. And you can use that, or this not ohm, sorry. This is ohm, this is millivolts. So this is also going to be milliamps. So you can do that and convert it. You'll find that the magnitude is the same as, the magnitude and phase are the same as what we calculated. So they work both ways. Our next problem seems a little intimidating at first with all these components basically, but it's really not too bad. So we're given these impedances at the frequency is unknown. I believe it's 1500 radians per second, but it's not important. We're just given these impedances. And we're going to find out what the currents IA, IC, and IG are. Now we're given that IB equals 25 milliamps with a phase angle of 0. We're also given the impedances for each of these branches, and we can use them to derive sort of like the equations and all that business, right? So we can say that IG is going to be the sum of all these currents, IA plus IB plus IC. That'll be our KCL. And we're going to start with, I'll go ahead and do the impedances first, and then we'll do our equations. So we're going to find equivalent impedance right here. It's pretty simple. That's going to be 500 plus 250J. So let's say that IA is, if I call this, go ahead and label the whole circuit. I'll call this ground. It's not actually ground. Hold on. It's our 0 volt reference, but we'll just say that's our ground. And here's VG, and this will become minus J50. Alright, so we can say that IA is VG minus 0 over 500 plus J250. IB is going to be VG minus 0 over the impedance, so this is going to be 2000 and minus J1000, and IC is going to be VG minus J250, so that's going to plus J50 over 1000. So using all this information, we'll be able to use these to solve for our known value, which is VG, and find out its currents. So anyway, if we say that IA VG blah blah blah. Sorry, my notes I wrote were a little bit confusing even for me now. Okay, so I went ahead and calculated all this, I think, with my calculator. Oh, yeah. Since we're given VG, or IB, we can go ahead and plug that. So IB is 25 milliamps. So if we multiply it by its impedance, so 2000 minus J1000 is going to be like V equals I times Z. I'll find VG and find that VG is, let's see, 50 minus J25 volts, which is going to translate to 50, magnitude of 56-ish, it's like 55.9 minus 26.5 degrees phase. So we're going to use that to find out the rest of our currents. I'll start with IC. So IC is going to be 50 minus J25 minus minus 50, so we'll just do plus. We already put it in the expression. J50 over the impedance, which is 1000. So that ends up being 0.05 plus J 0.025 amperes, or 50 plus J 25 milliamps, which equates to 55.9 degrees, the phase angle of 26.5. And using that, we can go ahead and find out our last current in here, IG. We're going to add up all of these currents. So IG is going to be IA plus IB plus IC, so it's 25 phase of 0 plus 56. I'll just leave it like that. 56 minus 26.5 degrees plus 55.9 degrees, phase angle of 26.5. So that's IB, IA, and IC respectively. Now we got to convert these to the polar form, or the rectangular form, first before we can move on. So that ends up being IG is, go ahead and put this right here for all these. So you're going to have 25 plus 60 plus 50. Those are the real components of each of these. We're only going to have two imaginary components because we have a 0-degree phase angle on one of these. This ends up being 135 minus J 55 milliamps. So if we convert that back into the phasor, remember our omega, actually I think the question gives it, yeah, see if omega is 1500 radians per second. We can go ahead and convert these phasors to time. So IGT is going to be the magnitude of this, which is 145.7 cosine of 1500 t at a phase angle of minus 22.2 degrees. These will be milliamperes. IA of t is going to be 56 cosine 1500 t minus 26.5 degrees milliamperes. IB is going to be 25 cosine 1500 t minus 0, so just that, milliamperes. And ICT is going to be 55.9 cosine 1500 t minus, or plus rather, 26.5 degrees milliamperes. So yeah, it's not too bad. You just, once you get it into the rectangular form, convert back to polar, find magnitude, find the phase, do it for all of these, and use your formulas to convert back and forth. So this problem, we've got to find out what this unknown impedance is right here, and we're going to do that. We already know the voltage drop across it because we're given both the voltages in the problem, V1 and Vg. I chose to put my plus over here. It doesn't really matter. We just need to know the difference across it. We also need to know the current flowing through it, which we can calculate. We can find out what I2 and I4 are because we're given Ig. And then we'll be able to find out the impedance using, effectively, Ohm's law. Now we're a little bit fortunate. The problem gives us I4 right away because we're given what V1 is. We're also given the impedance of the capacitor at the given frequency. So we already got one of those things squared away. Now we just need to find out what I2 is now. The expression, I made a little bit of a mistake right here. There you go. Let me go ahead and rewrite that quickly. The other one was right, it's just too small. So V2, and then this one, I3, is V2 over J5. So if we can find out what V2 is, then we'll be able to find out what IZ is. So if we use our second KCL equation, I1 plus I2 equals I3, we're going to have 100 minus J50 minus V2 over 20 plus 140 30J minus V2 over 12 plus J16. Now, if you're curious where this came from, I just added up these two impedances. They're in series, and we don't really care about this voltage over here. And if we did, we could get it by finding the voltage drop across this or this using the current we calculate. So anyway, keep moving. V2 over J5. Punch that into my calculator. I end up getting V2 is 40 plus J30 volts. And using that, we can find out what I2 is. So I2 is going to be 140 plus J30 minus 40 plus J30. Make sure the parentheses, just in case, so you don't forget the minus. J16. That ends up being 3 minus J4 amperes. So using that, we can find out what IZ is, because we know IG. Now use our first KCL, we'll just solve for IZ, so IG minus I2 minus I4 is going to equal IZ. So that is 30 plus 20J minus 3.4. Let's double check. Let's see, 3.4. Yeah, minus 3.4 plus 4J. 3 plus, yeah. So I get an answer for the current is 30 plus J10 amperes. So now we know the current flowing through the impedance. We also know the voltage drop across it. VZ was 40 plus J30 volts. So we can find the impedance by taking VZ divided by IZ is going to equal RZ. So let's see, 40 plus J30 volts over 30 plus J10 amperes ends up being 1.5 plus J.5 ohms, or 1.58 with a phase angle, or magnitude 1.58 and a phase angle of 18.43 degrees. And that is our impedance. In this problem, we've got a variable capacitor right here that's adjusted until the current IG, which is the current through the whole circuit, is in phase with the source voltage VG at this given frequency. So basically what we got to do is we got to find the impedance of this whole circuit, and we want to find a value for C that makes the imaginary component of the impedance 0. So to do that, we're going to first find the equivalent impedance. So we're going to need to know the angular frequency, which is given as 5,000 radians per second, which means that ZL is going to be 0.8 times 0.8 times 5,000 J, so that's going to be 4,000 J ohm. And our capacitance, or our capacity of impedance, is going to be 1 over J 5,000 times C, our unknown value. Which means that if we do the Z equivalent, we'll just do, this is a series and parallel combination. So we're going to have that in series with this parallel combination, 1 over 10K plus 1 over J. This actually is going to become 1 over J 5,000 C, so reciprocal is going to be just that, J 5,000 C. So this is going to be Z equivalent. It's going to end up being, let's see, we're going to get the imaginary component. We only really care about the imaginary component, so I'll just say the J part. So we know the J part is going to end up being 4,000 minus 10,000 divided by, 10,000 divided by 5 million C minus the J. So we're going to rationalize, or not rationalize, we're going to multiply this by the conjugate, there's complex conjugate. So it's going to be plus J over 5e7 C plus J. That ends up being J 4e3 plus 1e4 minus J 5e11 times C, our unknown capacitance still, 2.5 E15 C squared plus 1. So that's the part of this business. So our Z equivalent is going to end up being 1e4 over 2.5 E15 C squared plus 1. That's going to be a real component. I'm going to separate the real and imaginary components so we can solve. So this is a real right here. And our imaginary is going to be 4,000 plus, or not plus, minus 5e11 times C over 2.5 E15 C squared plus 1. So if you punch these values into a calculator, we're going to solve for, say if you take this imaginary, you set the imaginary part to equal 0, and hit solve, you're going to get that C can be what? Since this is a quadratic equation, we're going to get 2 possible values. You can either get 40 e minus 9 or 10 e minus 9. Both are equally valid. I don't believe there's an extraneous solution to this particular problem. So that's going to be 10 nanofarad or 40 nanofarad. So I believe the question asks, give the steady state expression for Ig when the C value has been found in A. So basically we need to find out what the impedance of this whole circuit's going to be at these given values. Now, we know, because we calculated it, that this part is going to tend to 0 if we use these values for capacitance. So all we have to do is take the real one down, and we're going to calculate an impedance for each case. So the first case, I'm going to do the impedance, I'll call it Z1 for case 1. It'll be the impedance for a 40 nanofarad capacitor, so 1E4 divided by 2.5 E15, and then we'll plug in, I'll just leave it as C squared for now, plus 1. Plug that into a calculator with this being 40 nanofarad. Going to get 2 kiloohms with a phase angle of 0, which we expect. So we could just say 2 kiloohms. And the second case will have an impedance that'll be fairly similar. 2.5 E15 C squared plus 1, except we have 10 nanofarad right here. That's going to end up being 8 kiloohms, phase angle of 0. So 8 kiloohms. Now if we want to find out what our values for VG are, or IG rather. So let me actually use the capital to be a little bit more clear and still in the phasors. So our source voltage, what is it, VG is 80 because phase angle 0, so VG is going to be 80 phase angle 0. So we're going to do 80, 0 divided by, I'll just say ID1. This is going to be 2K phase angle of 0. That's going to end up being 80 divided by 2 is 40 divided by 1,000 milliamps. So, and then 0 minus 0 phase shift, so 40 milliamps. And IG2 with the 10 nanofarad capacitor, we're going to have 80 phase angle 0 divided by 8K phase angle 0, going to be 10 milliamps. So our time domain version, our time domain expression, say IG1 is going to be 40 cosine of angular frequency is 5,000, T phase angle 0 milliamperes, and IG2 magnitude is 10 milliamperes cosine 5,000 T phase angle is 0 milliamperes. So this problem, we're returning to the Norton and Thevenin equivalence. Now, this one isn't actually too bad, because it's basically a voltage divider. And you could say it's an impedance divider if you want, but we want to find the V Thevenin, or V open circuit voltage here. We're given our VG. If we call this our ground, we draw that a little bit better. Okay. So we're given get VG and we'll call this V open circuit. Okay. So we need to find, or the sinusoidal source is developing this voltage. Now, I'm going to translate that quickly to cosine. So 50 cosine 400 T minus 90 degrees Once again, you can do that because sine and cosine are orthogonal to each other, so the phase would be 90 degrees. Anyway, so we also got to calculate the impedances, and we're going to use them to find out the voltage drop across them, basically. Now, at this particular frequency, the inductor has an impedance of 160 ohms, I should say 160 J ohms, and the capacitor has an impedance of minus 80 J. Now, we can find a parallel combination. I'll call that Z1. That'll be ZL parallel with ZC. That's just going to be 1 over J160 plus 1 over J80 so minus 1. I got 160 over J. So if we multiply that by its complex conjugate, you get minus 160 J. Ohms is our Z1. So basically the reason why I did that is because I want to form kind of like an impedance divider and use that to find out what VTEM is. So here's our Z1, and this is going to be 320 ohm. So I want to find this voltage right here. Now I have a given voltage. I'm going to convert this one to a phase or rectangular form. So the cosine of minus 90 degrees is 0. So the real part's going to be 0. So I'll say VG is 0, and then there's the sine is minus 1, so it's going to be minus J times the magnitude, so J50 volts, which means that VTEM, if this is VG, then VTEM is going to be VG times Z1, which is minus J160 over the combination of the impedances in series. Just a straight up voltage divider equation. This would be minus 8,000 divided by 220 minus J160, which ends up being minus 20 minus 10 volts, or J10 volts. So that is our VTEM. Now to calculate the Z equivalent, we're going to look at the terminals, and I believe we have a voltage source. Is that right? Yes, voltage source. So I'm going to go ahead and draw the little boxes again, this time with the source shorted out, because an ideal voltage source is going to have 0 internal resistance, or 0 internal impedance in this case, because we are dealing with a frequency. It's not just straight DC. So AAB, and we know already this is, I believe this was the capacitor. No, that was the inductor. Okay, so that means that this impedance is going to be J160. This is going to be minus 80J, and this is 320 ohms. You may notice these are all share common terminals, so they're in parallel with each other. So we can find the ZTEM as the parallel combination of all these. So 1 over 320 plus 1 over j minus 80 plus 1 over j160 to minus 1. That means Z10 is 64 minus j 128 ohm. Now this is only valid for this frequency given, which is 400 radians per second. This impedance will change with frequency, but in this case, it's like this. So at this particular frequency, the reactance of the capacitor is dominating. That's why there's the minus here. So when we're drawing the final circuit, the equivalent circuit, we could draw a capacitor and a resistor in series with the source, but I'm just going to draw the little box. Either way is correct. It's just I prefer to use the little boxes when dealing with the impedance is. Anyway, so I'm going to convert Z-Thevenin and V-Thevenin into their phasor representations. So the magnitude of 20 or minus 20 plus minus J10 is going to end up being 22.3 at a phase angle of 206.5 degrees. And this reactance, or this impedance, I should say, resistance and reactance together, is 143 for the magnitude, and the phase angle is minus 163. So our equivalent circuit is going to be something like this. So this is going to be 22.3, 206.5 degrees, and then volts, 143 phase angle of just 3.4 ohm. That's our equivalent circuit. So for this problem, we're going to find the Norton equivalent of this circuit from these two terminals A and B. So I went ahead and labeled it already. I'm going to go ahead and make this a short, which means that V3 is going to be 0 volts as well, and a current right here, I short circuit. Alright, so KCL, we got two KCLs. We got I1 plus I3 is, before it was equaling 0, because there was nothing, but we got I short circuit, leaving that node now, and I2 I2 equals I3 plus I4. Now we use our equations. We can say that I1 equals V1 minus 0 over J 20 ohm. I2 is going to be V1 minus V2 over 20 ohms. I3 is going to be V2 minus 0 over 40 ohms. And I4 is going to be V2 minus 0 over J 16 ohms. Okay. So to find I short circuit, we need I2 or I1 and I3. And we can find those out, and we can find out these values for the voltages. Now, when I solved this, I found it helpful to notice that this was effectively a series and parallel combination. There's a series resistance and then a resistance in parallel with this inductive impedance, because they are both going to 0 volts, the top and bottom node. So I went ahead and did a sort of a Z equivalent for finding for the current I2, because I2 is split between I3 and I4, the 40 ohm and the J16 ohm impedances. Anyway, so ZQ, I call it ZQI2. Basically just adding them all up to make it easier to find V1, and once we find V1, we'll go to find V2. So there's 20 ohms in series with this parallel combination, so 1 over 40 ohms plus 1 over J16 minus 1. That ends up being 100 plus J120 over 5 plus J2. Now, to plug that in, say that this is, we'll do the source current here. I forgot one more KCL. So there's the source current. We're given as 0.14 plus J2 amperes equals, I should get rid of the A. That would be confusing. Equals I1 plus I2. Anyway, so this is going to be so like the impedance seen by the total impedance seen by the current I2. So I'm going to have 0.14 plus J2. That's our current source. I just pulled the 0.1 out. So the complex number would be a little bit more round. V1 over J20, that's I1, plus I2, which is going to be the reciprocal of this impedance, because we're just going to be dividing it by ZQI2. So in other words, hold on. In other words, it'll be 5 plus J2 over 100 plus J120. So I punch that into the calculator, get 9.2, or V1 equals 9.2 minus J 3.6 volts. And using that, we can find out what the value for I2 is. So I2 is going to be 9.2 times blah, 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 times that impedance, or divided by that impedance, so 0.22 minus J 0.26 amperes, which means that we take I2, we can solve for V2. So V2 is going to be, let's see, because we know V1, and there's the V2, and we know that the impedance over here is 20 ohms. So this is a known value. This is a known value. This is a not known value, but we can find it with a little bit of algebra. Basically, hold on, my pen's not cooperating. I'll be right back. Hold on. Okay, so now we can go ahead and find V2. If you take I2 and multiply it by 20, get 4.4 minus J 5.2 equals 9.2 minus J 3.6 minus V2, which means that V2 is going to equal 4.8 plus J 1.6 volts. So now we know V2, we can go ahead and calculate I short circuit. Now I short circuit is going to be the currents I1 and I3 put together. I1 is 9.2 minus J 3.6 volts divided by the impedance minus 20 or J ohms plus 4.8 plus J 1.6 over 40, which ends up being 0.3 plus J 0.5 amperes, which if you write it in phasors, magnitude is 0.58 with a phase angle of 59 degrees. So now we got to find the equivalent, the Norton impedance, which is not too bad. I gotta do my boxes again. I gotta remember to open up the current source because ideal current sources have infinite internal resistance, or infinite impedance in this case. So 40, J16, 20, and minus J20. So this is a series combination which is going to be in parallel with this, which is going to be in series with this. So our Z equivalent is going to be something like this. Z Norton is 1 over 40 plus 1 over 20 minus 20 J minus 1 plus J16, which means that Z Norton is going to end up being 16 plus J8 ohms, or in the phase vector form, 17.8 is the magnitude with a phase angle of 26.5 degrees. Also still. Now, kind of like the last one, we've got this, instead of it being a minus J, it's a plus J. That means that the impedance at this particular frequency, I don't believe it's given, but at this particular frequency, the reactance is, the inductance will, or the inductive reactance will dominate. It's a primarily inductive impedance seen here. So this is probably at a high frequency, but we don't know. But we can go ahead and draw the equivalent circuit as the current source with the current magnitude of 580 milliamps, approximately, the phase angle of 59 degrees, in parallel with the Norton impedance, which is 17.8 its magnitude, and the phase 26.5 degrees, terminals A and B. Now, if you wanted to, just like the last one, you could write that in series with inductor, since it's inductive at this frequency, but I prefer to use the boxes. Alright, so for 9.48, we're going to continue finding Norton-Thevenin equivalent circuits, but this one has a dependent source on it, so we're going to basically solve it twice and use that to find out what the Zn is going to be. Now, I've been doing a lot of these using my calculator. There's nothing wrong with that, but if you guys prefer to do it by hand, or you want to at least learn a little bit about how to do it, I'm going to do pretty much all of this problem by hand. Alright, so one, blah, blah, blah. Okay, so I'm going to label this voltage, call this V2, call it this. I'll just call this, because we already know what it is, I'll just call this V1. And then this is going to be minus 40 plus J40 volts, because I'm going to call this ground. Okay, so that's going to make our equations KCL, I short circuit plus I2 is going to equal I1. In other words, we could say I short circuit is I1 minus I2. It's the same equation, just a different form, because we're going to need to know I short circuit ultimately. So anyway, I1 is minus 40 plus J40 minus V1 divided by 10. And I2 is V1 over J10. And we got to deal with the dependent source. So Vx is going to be, let me go ahead and shift this around a little bit just to make a little bit more space. So move I2 over here. Vx is going to be minus 40, or actually, yeah, I'll just leave it as minus 40 plus J40 volts minus V1. Because here's our plus, here's our minus. You can also say, if we want to do this symbolically, real quickly, if I call this up here VG, just to make the substitution a little bit simpler, I'm going to say that VG is going to equal minus 5 times Vx, or Vx, sorry, Vx, which is, or not VG, I'm sorry, V1. It's going to be minus 5 times Vx, so that's going to be 5 Vg minus 5 V1. And remember that this is Vg. I'm just doing it symbolically to make it a little bit more clear what's happening. And also so I don't make a mistake. So 5V1 is going to equal 4 Vg, which means that 5/4 of Vg is equal to V1, which means that if Vg, which we know is minus 40 plus J40, then V1 is going to be minus 50 plus J50 volts. Okay, so we're one step closer to finding our I short circuit. We know what we can find I1 now because we got the voltage drop across that resistor and use that to, in concert with the voltage V1 to find out what I2 is, and then subtract to find I short circuit. So I1 is going to be minus 40 plus J40 minus 50 plus J50 divided by the impedance, which is 10 ohms, which ends up being, let's see, this is minus 40 plus 50, and then same thing both times basically, That's going to be that over 10, so 1 minus j. So I2 is going to be minus 50 plus j50 over j10 equals minus 5, yeah, minus 5 minus j5. All right, so if we take expression, let's do I short circuit equals I1 minus I2. If I1 is 1 minus j and I2 is minus 5 minus j5, that means that I short circuit is 6 plus j4 amperes. Okay, so we've got half of what we need to find the Norton equivalent circuit. Now we need to find the Norton impedance. So what we're going to do here is we're going to find the Thevenin equivalent, the open circuit voltage, I guess. Anyway, so I'm going to redraw the circuit. Instead of connecting that, I'm going to leave it open. So we're going to have this, and then dependent source right here. And the polarity is like this. This will become important in a minute. Okay. This will be VOC. I'm still going to call this V1. Still call this minus 40 plus 40 J volts. V1. This is still going to be ground. Okay. And then this impedance is 10 ohms, this impedance is minus j 10 ohms, and this voltage source right here is going to be 5 times Vx, which is the voltage drop across this resistor. Okay. Now it may be tempting to say, oh, well, there's no current flowing through here, so the voltage over here is the same. Well, it isn't really. If this was not a passive component, then you could say that. But this is actually supplying power to the circuit, or maybe it's dissipating power. But it's basically not a passive component. It changes how it behaves. So we can find out. We can't use the voltage divider to find out this voltage right here. We got to do a little bit of math. So V open circuit is going to be whatever the, see, here's V1 or Vx, 5 times Vx plus V1. That's because of this sign right here. Basically, this is just higher. It's increasing over to here. So if this was 5 volts or whatever, and this voltage dropped by 1 volt, that means that this would be 10 volts. So let's go ahead and solve it. So if there's no, the one thing we can say though, if there's this current is still I1, this current is I2, this current is 0. So I1 equals I2. If we come up with an expression for I1, that's going to be, I'll just write it as VG. We know it's minus 40 plus 40J minus V1 over 10. And I2 is going to be V1 minus 0 over J10. So we're going to set those equal to each other. Say that minus 40 plus J40 divided by 10 equals V1 over J10. And doing a little bit of algebra, you'll be able to find out that V1 is going to be J40. Now, like I promised earlier, how we'd be able to find out this stuff by hand. So this is what my calculator gave me. I'll show you how to do this by hand. First thing I'm going to do is multiply, I'll write this out again, over 10. I'm going to multiply this by its, this is minus J10. So this is minus J10, and then V1. I'm going to multiply this by its complex conjugate. So that's going to become minus 40 plus J40 over 10 equals V1 times J10 divided by J minus J times J. So this is going to become 1 because negative 1 times negative 1 is 1. Anyway, so 10 times 10 is 100, which means that it's going to end up being, I'll just multiply everything by 10 in a minute, or 100. Yeah, I'll multiply everything by 100, just to give you the denominator. So this is going to become 100 divided by 10 is 10, so 10 times 40 is 400 plus J400. Oh, I'm sorry, did I forget to write something? Minus J, cool. I did. Hold on. This answer is still right, I just made a little slip in my notation. That's I1. This is still I1. Okay. So this is going to become 10 or minus 10 V1 equals J10 V1. Okay. So now I'm gonna pull the 400 out of here. I'm gonna have minus 1 plus J. I'm gonna move this to the side. That's gonna equal, pull the V1 out, 10 plus J10, which means that if we divide it over, we're going to find it. So 400 minus 1 plus J divided by, let me just go ahead and pull the 10 out. So 10, 1 plus J. So 10, 1 plus J equals V1. And actually, I'll shift this around a little bit because I already have V1 by itself, so I'll put it over here. Now I'm going to multiply top and bottom by the complex conjugate once again. So that is going to be C40 and then 1 on top. Let's see, minus 1 times 1. Oh, this is plus 1. Let me just double check, make sure I didn't make a mistake. Let's see, plus 1, plus 1. Yeah, this is plus 1. Okay, plus 1 plus J. So 1 times 1 is 1. And then we're going to have plus J and plus J. So it's going to be plus J2. minus 1, because j times j is minus 1. And it's going to be divided by, let's see, 1 minus j plus 1. So it's going to end up being j40, right? Yeah, j40. That's going to be 2 divided by 2. So there you go. That's how your calculator is basically doing it. So that's the value for V1. And using that, we'll plug it in with our original expression. So this is like Vx is going to be minus 40 plus j40 minus j40, which is this is our V1, this is our VG, our source voltage. So that means that Vx is 40, yeah, minus 40, because 40 or plus 40 minus 40, 0, so it's become minus 40 volts. Which means if we use a dependent source to the open circuit, it's going to be 5 times Vx plus V1, which means 5 times 5 times 40 is minus 200, plus V1, which we know is J40. Okay, so that means that Vthevnin is minus 200 plus J40 volts. Now we're going to go ahead and find Z Norton. So it's V open circuit over I short circuit minus 20 or minus 200 plus J40 divided by 6 plus J4, 6 minus J4, we're just going to do the complex conjugate. That's going to end up being minus 1200 plus J240 plus J800 plus 160 divided by 336. So 6 times 6 is 36. 4 times 4 is 16, so 16, so 52, which means that Z Norton is going to be minus 20 plus J20 ohm. Okay, so the reactance is primarily inductive at this particular frequency. But I'm going to go ahead and draw the equivalent circuit. So V or I short circuit with 6 plus 4J. So let me go ahead and convert that to phasor real quickly. 36 plus 16 square root of 52, and that's 2 radical 13. So this will be 7.2-ish. The phase angle arctangent of 2/3. The first quadrant is 34 degrees-ish. And this is going to be, what's square root of 400? 400 square root is 20. Okay, and then the phase angle is going to be, let's see, that's minus plus, so that's going to be 135 degrees. Yeah. And we still have our terminals A and B. So now we've got to find the impedance, the equivalent impedance across the terminals A and B. when the circuit is operating at an angular frequency of 100,000 radians per second. So to do that, first we need to calculate what the impedances of the inductor and capacitor are at this frequency. So ZL is going to be J60 ohm, and ZC is going to be minus J25 ohm, using your standard formulas. And now we actually have to find out what the values for these voltages and currents are, so we can find out what the voltage drop is for all this. So to do that, I'm going to connect a test source. Going to be 1 volt with a phase angle of 0. And I'll call the voltage across. If I say that this current right here is I1, this current is I1, and that this current is I2. If I say this is 0 volts, this is going to be V1, V2. Okay. So we'll do KCL. I delta plus I1 equals I2. Should be the only one equation we need for that. I1 equals 1 minus V1. 1 is from our test source. It could be any number, but I chose 1 because it's easy. I delta is going to be minus V2. So 0 minus V2 over 30. And I2 is going to be V2 over the impedance of the inductor at this frequency, which is J60. Alright, so we have the dependent source we have to deal with. The voltage difference across it is going to be V1 minus V2. By definition of what we just did, it could be whatever we named it, but I chose V1 and V2. Anyway, so I delta is V2 minus V2 over 30, so minus V2 over 30 times 5 is going to be minus V2 over 6. It's going to equal V1 minus V2, which means that minus V2 equals 6V1 minus 6V2. If we simplify that, 5, 6, V2 is going to be V1. So we use that substitution to find out what I1 is. Alright. So 5, 6, or 1 minus 5, 6, V2, this is I1 over J25 minus, let's see, it's going to be plus, so it's going to be plus minus V2. I'll move the minus out front over J60. No, J30. Or this is just the, this is I delta, right? Okay. And then V2 over J60. I'm going to build a little bit of a space there so I don't overlap. So anyway, my calculator gives me that V2 is 0.48 plus J 0.96 volts, which means that multiply that by 5 and divide it by 6, V1 is 0.4 plus J 0.8 volts. So using that, we can find out what I1, we can find out what I1 is. So I1 is going to be (1 minus 0.4 plus 0.8 J divided by the impedance minus J25. So that ends up being 0.032 plus J 0.024 amperes. And if we make our V test divided by I1 is going to be the ZAB. And we know this because I1 is the current that enters and leaves this network. So anyway, if VT is 1, so 1 divided by, let me actually convert this to milliamps. So this is going to be 32 plus 24 milliamps. So that's going to make our top. I'll just make this 1,000. 32 plus J24. End up getting 20 minus J15 ohms. And that is the ZAB for this circuit at this frequency. Alright, this problem says to use node voltage, but we're going to use the universal method. I1, I'll call this I2, and I'll call this I3. We know that this is going to be VO over 8. If I make this ground, which I will, so we need an unknown voltage here. I'll call this V1. Unknown voltage here, VO. Alright, so with KCLs, 25 milliamps going in, IO leaving, I1 leaving. Second one, 16 IO entering, or sorry, leaving, I2 leaving, plus I3 leaving, all equals 0. This is valid, don't worry. And equations for components. I1 equals V1 over 40. IO is going to be V1 minus VO over 8 over J20. I also write it 8V1 minus VO just because I think that makes it a little bit easier. And I2 is going to be VO over 50. I3 is going to be VO over minus J25. Alright, so this one, the math is a little bit hairy. So try to stay with me. I know it's kind of, this one's not that easy to follow along with. 25 milliamps. V1 over 40 plus 8 V1 minus VO over J20. We're going to make that, just kind of multiply. We want to get the same kind of denominator so we can combine them. So I'll multiply the top by J, top and bottom by J. So it's going to become J40. It's basically the same as dividing and multiplying by the same number. And I'm also going to make this, multiply this by 2. So that way we can get the denominator to be the same sort of magnitude. So 8V1 minus VO over J40. Combine the terms, so 25 milliamps equals JV1 plus 16V1 minus 2 VO divided by J40. That ends up being multiply this both sides by 40 J. So 1 over 40 is 85 milliamps. So it's going to be J equals V1. I'm going to factor out the V1, 16 minus V1, or plus J, sorry, plus J, minus 2 VO. So I'm going to have this as my first equation, and we're going to relate this to the second equation and solve. So the second equation I'm going to derive using the other KCL, 16IO, 8V1, VO over J20, plus VO over 50, plus VO over minus J25, all equals 0. So I'm going to multiply in the 16. This will become 128 minus 16 VO, sorry, 128 V1. Over J20 plus VO over 50 plus VO over J25 minus J25 equals 0. So if I take this whole thing, I'm going to divide everything on the top by 2 just so I can get I want to get this to be a little bit easier, so I'll make it not minus J10, but I want to make it J10. So to do that, I'm just going to divide the top by 2, which we can do because they're all factors of 2. 64 V1 minus 8 VO over J10 plus VO over 50 plus VO over minus J25 equals 0. And the reason I'm doing that is because complex numbers are a little bit harder to normalize the denominators for, find sort of the greatest common denominator, etc. So anyway, this is going to simplify to multiply everything here on the top by 5, get minus 320, or I get 320 V1 minus 40 VO plus J VO minus 2 VO all over J50 still equals 0. And using my calculator, combine these equations, have them solve. I get V1 equals 0.8 plus J0.6 volts, which means that VO is going to equal 4 plus J4 volts. And using these values, we can find out what IO is. So IO is going to be 8 times 0.8 plus J0.6 minus 4 plus J4 divided by the impedance, not minus J20, which means that IO is going to equal 0.005 minus J 0.0, not 0.015 amperes. Or, in other words, you can say in milliamperes, so we'll just do IO is 5 minus J15 milliamps. Now, I believe the question asks for the both rectangular and polar forms. I'm going to double check. Oh, well, it doesn't. Anyway, we'll just convert it real quickly. So VO is going to be square root of 32. Its phase angle is going to be 45 degrees. Its first quadrant. and IO is going to be 15.8 as the magnitude. The phase angle of minus 71.5 degrees, because that's in the fourth quadrant. I should actually, can't forget the unit. There you go. Alright, this question once again asks to use the node voltage method, but we're not going to do that. We're going to do universal, because we've been doing this whole time. Why change it now? So I'm going to call this current I1, call this current IO, and I delta's already been labeled. So we only have one voltage in the circuit, which ends up being VO. Call this ground. I want to find the phasor voltage VO and express it in polar rectangular form. This is pretty easy. Once we get one, we just convert it. Anyway, so KCL got 10 plus J10 amps going in, I delta leaving, I1 leaving, and IO leaving. Equations for components. Call I delta is V1, or not V1, sorry, VO over minus J8 IO is VO over 5, and I1 is, let's see, VO minus 2.4 I delta over J4. Okay. So now we gotta find, well, we can just plug it in straight away. Let's go ahead and do that. So I'll use our KCL, 10 plus J10 equals VO over J8 plus VO minus 2.4 times VO over J8 divided by J4 equals, or not equals, sorry, that would be not right, plus VO over 5. Okay, so it's going to simplify a bit. It's going to be 10 plus J10 VO over J8. And I'm going to try to pull this J8 around just to make the math a little bit easier. So we're going to have J8 VO minus 2.4 VO divided by J4 times J8, which is going to end up, or sorry, minus J4. Isn't it? Let me double check. No, it's positive J4. It's minus J8. Okay. So I'll leave the minus there, it's fine. Okay, so this VO over 5. Now this looks confusing, but it's really not too bad. Just remember J times J, so minus J times J is going to be minus 1 times minus 1, and 4 times 8 is 32. I'm also going to simplify this. Let's do the conjugate. So let's see. 1 over J8, J8, J8. That's going to be J8 over 1 or -1 times -1 times 64. So it's going to be minus j over 8. Okay. So let's go ahead and get into final form. JVO over 8 plus 8 minus 2.4 VO 2.4. No, sorry, I did it backwards. Okay. Minus 2.4 plus 8J VO over 32 plus VO over 5 equals 10 plus J10. So if I punch that expression into my calculator, I get VO equals J80 volts, which also is 80 is the magnitude, the phase angle of 90 degrees volts. So I got the rectangular and polar form. Okay, so that is the last solution for this class. I hope that my solutions throughout the semester have helped you to understand what's going on, maybe taught you a couple of things, and thank you for being here with me. Good luck on your exams.